Welcome back to the effect. Now, we've been talking about difference in differences for the past couple of videos, but in a largely conceptual manner. But we probably want to actually estimate a difference in differences effect. Well, how can we do that? So we're going to do just a couple different kinds of ways. The first way we're going to do it is the very most basic. It is the four means approach to difference in differences. What is difference in differences all about? Well, we need some sort of estimation method that will allow us to compare the before to after for the treated group, calculate the before to after for the control group, and then compare those two before to after differences, subtracting this control group's before to after out of the treated group's before to after to get our difference in difference effect. Now, one way we can do this is just literally doing it. I can calculate the average after for the treated group and the average before for the treated group, and I can see how much that changed. I can subtract one from the other. I can do the same over here. I can calculate the average outcome after the treatment went into effect for the control group and the average outcome before it went into effect for the control group and subtract one from the other. Now I have the before to after difference over here. I got the before to after difference over here, and I can subtract one from the other to get difference in differences. We can see this in effect with an example of a study from Kessler and Roth, and they were looking at organ donation rates. So in the United States, it is an opt-in system to be an organ donor. When you sign up for your driver's license, they say, hey, do you want to be an organ donor so that when you die, somebody else can use your liver or whatever? And you check a box for yes, or you leave it blank. This is an opt-in system. You have to say that you want to be an organ donor, which leads to much lower rates of organ donation than in other countries that have opt-out systems where you are assumed to be an organ donor unless you say that you don't want to be. So there is a variant, however, on opt-in versus opt-out, and it is forced choice. And for what forced choice is it's not they'd say, hey, do you want to be an organ donor? Say yes for yes, or ignore it for no. Instead, you actually have to respond to the question. Say yes for yes, no for no. So it's the same thing. You still have to opt in, but it forces you to say no if you want to say no. Sort of a mix of opt-in and opt-out. So what they want to know is, does having this forced choice increase organ donation rates? So what they do is they look at the state of California. California put into place this forced choice format in July of 2011. And Kessler and Roth compare the organ donation rates in California against a bunch of other states that did not have this forced choice format and were perhaps comparable to California. And what they're looking at is, hey, does the organ donation rate in California increase by more than it does in other places? So we can look at this graph right here. So what we have are, you can see those four lines. We sort of have four lines. We have a dashed line before and after the cutoff of July 2011. We have a solid line before and after the cutoff in that top left area over there. These are our four means. The solid line is the average of those three California points. I've got 3/4 of California organ donation data before the treatment went into effect. I've also got 3/4 of California donation data after the treatment went into effect. And if you take the average of those points, you get that first solid black line before and the second solid black line after. That is the treated group average after and the treated group average before on the right and left sides of the graph, respectively. So what I'm doing is I'm seeing how much that dashed line jumped at the point where the treatment went into effect. And I'm going to say that, hey, that's how much California would have jumped anyway. And I'm going to subtract that. I'm going to push down the lines so that the dashed lines meet up exactly and the California line gets pushed down by an equivalent amount. And what exactly are these numbers? Well, these are the four means that I mentioned, right? So what do we have here? So the control group, its organ donation rates went up. It went from 44.5% organ donation rate to 45.9%, a 1.4 percentage point increase. So it looks like in the control group, organ donation rates were actually going up over time. So we would have expected that in the absence of any policy, California's organ donation rates probably would have gone up over time as well. How much did they go up by? Well, actually, California's organ donation rates went down. They actually went down from 26.3 percentage points to 27.1 percentage points, which is a reduction of 0.8 percentage points. So California's organ donation rates went down. We could say, well, maybe everybody's organ donation rates were going down, but that's not what the control group says. Control group says that everybody else was going up. And so if we expect that California would have gone up by the same amount, by 1.4 percentage points, but it actually went down by 0.8 percentage points, well, it looks like the policy made things worse by 2.2 percentage points. Not so good. How can we actually work this out to get an estimate? Well, it's just those four means that I talked about, putting them in the right order. I'm doing the before to after difference for California. So I've got 26.3 percentage points after minus 27.1 percentage points before. I've got the before to after difference for the control group, which is 45.9% after minus 44.5% before. So that is negative 0.8 percentage points over here. That is positive 1.4 percentage points over here. Negative 0.8 minus 1.4 is negative 2.2. And that is the effect that we have estimated using our four means approach. However, there are some obvious limitations to doing it this way. I mean, it'd be hard to get a standard error using it in this particular method. It's going to be really difficult to go beyond as 2 groups and 2 treatment time periods. What if I have data for more than 2 periods or data for more than 2 groups? What am I going to do? Well, we're going to take this into the realm of a regression, first to let us get standard errors, and then we're going to allow ourselves to generalize beyond 2 groups and 2 time periods. So we have 4 means that we need to estimate. We can just set up a regression in a way that it will estimate these 4 means for us. That brings us to this regression equation. So what I'm doing is I'm regressing the outcome y on an indicator for being in the treated group, an indicator for being after treatment, and then the interaction between the two, which is also just saying, are you currently being treated? Are you in the treated group in the period where treatment is occurring? You notice we have 4 coefficients here, beta 0, beta 1, beta 2, and beta 3. These correspond to our 4 means that we were looking at. If I set treated group to 0 and after treatment to 0, that means that we are the untreated group before, which means that our beta 0 is our estimate of the average outcome in the untreated group before. That is our non-California states before the treatment went into place. What if I change treated group from 0 to 1? Well, now we are looking at the difference between the untreated group and the treated group. So the average outcome for the treated group before the treatment goes into effect is beta 0 plus beta 1, which means the beta 1 is the difference between the untreated and treated groups before. It's our baseline difference. What if I set treated group back to 0 and set after treatment to 1? Well, now we're comparing the untreated group before to after, which means that beta 0 plus beta 2 is our average for the untreated group after treatment goes into effect. Finally, you turn treated group to 1, you turn after treatment to 1. Now beta 0 plus beta 1 plus beta 2 plus beta 3 is our average for the post-treatment period for the treated group. So with combinations of these coefficients, we can get those 4 means that we talked about before. And in particular, beta 3 is the one that we are interested in. That is our difference in difference effect. It actually does the calculation for us and puts it in beta 3. Why is that the effect? Well, what is the effect of going from before to after? What happens when we change after treatment from 0 to 1? Well, for the untreated group, the mean goes up by beta 2, right? We go from beta 0 before to beta 0 plus beta 2 after, so it's an increase of beta 2. But for the treated group, we go from beta 0 plus beta 1 before to all 4 of them after. And so the increase from before to after is beta 2 plus beta 3. So if things increased by beta 2 for the untreated group and by beta 2 plus beta 3 for the treated group, well, what do we have? We have the time effect in beta 2, we have the time effect and the treatment effect in beta 2 plus beta 3, and we subtract out the beta 2 to leave us with just beta 3. That is our treatment effect. If that was a bit hard to wrap your head around, I'd recommend going back and reading the chapter or just review the stuff on interaction terms. This is a pretty standard application of an interaction term. Let's go a bit beyond that and say, well, what if we have more than 2 groups or more than 2 time periods? I mean, in the case of the organ donation example, we actually had 6 time periods. We had 3 quarters before the treatment and 3 quarters after. We had a bunch of different states. There's a bunch of different control and treatment groups that we might want to consider. And maybe we don't want to lump them all together into just control and treatment before and after. We want to allow their individual variation to shine. Well, that brings us back to the idea that we were talking about before. We're looking at within variation. I'm looking at the before to after change for the treated group. That's within variation. I'm looking at the before to after change for the control group. That's also within variation. What do we know about getting within variation? Fixed effects. We add a fixed effect for group, and that is going to give us part of the way there. So that brings us to this regression equation. This is y regressed on a fixed effect for group, alpha g, a fixed effect for time, alpha t, and a variable treated, which is 1 if you are in a treated group in a post-treatment period. So are you currently being treated? So the alpha g, the fixed effect for group, ensures that we are working within variation. The alpha t then says, hey, we're going to compare these different sources of within variation. We're going to subtract out all the shared time effects that we are estimating using that control group. We're going to subtract out those shared time effects, leaving us just with beta 1, which is the effect of treatment from before to after. This is probably the easiest way of estimating difference in differences using regression. Gives you nice standard errors. You can cluster the standard errors by group, which is a common thing to do because you might expect that those groups are more similar than they are between groups. And that is a pretty easy way of getting a difference in difference estimate. This is called the two-way fixed effects model. Now, I want to point out, before you rush off and get excited about this, is that all these methods I've talked about, all these different regression methods, the 4 means approach, only work if all of the treatments went into effect at the same time. So let's say you have multiple different treated states. If they get treated at different times, you'd be in trouble, right? So we had California here. California only got treated at one time period because there's only one California. But let's say we had a different state, let's say Wyoming, and they also switched to a forced choice approach. But California did it in July 2011. Wyoming did it in July 2012. Well, if you have that, you have what's called staggered treatment, and you can still work with it. We'll get to it in another video, but you can't use these regression methods to do it. It just doesn't work properly. All right, so those are a couple of different ways in which we can estimate a difference in difference model, either using just standard old 4 means to get the effect, which is a nice intuitive way to do it, or for something that's going to give us some standard errors and make things a little bit easier on us, especially in a multi-group or multi-time period context using regression. Thank you.